The backwards long jump, or BLJ, is perhaps the most famous trick in all of speedrunning. It's used in 4 of the 5 major categories in Super Mario 64, although it's most important for the game's shortest categories 0 star, 1 star and 16 star, where it's used to skip the 50 star door, and then again to skip the endless staircase leading to the last Bowser stage. It would save time in 70 star too, except it's banned as this is intended to be a no major glitches category. To perform the trick, you turn to face down the stairs, execute a long jump and then hold up on the control stick. While holding Z, you mash the A button to long jump backwards up the stairs and hope to clip into them and gain speed. I say hope because, unless you're superhuman, your BLJs could end up looking like this. If you look up ways to make BLJs more consistent, you'll find a lot of advice, but is any of it actually true? And what exactly causes the random nature of BLJs anyway? The first piece of advice is pretty obvious. Starting from as low down the stairs as possible just gives us more attempts before we have to go back to the bottom of the stairs and start again. But the rest of the advice will take a bit more work to prove or debunk. A long jump is performed by pressing Z while running to start crouch sliding, and then pressing A while Mario is sliding at a speed of 10 or more. Thanks to the Super Mario 64 Decomp team, we know the full code of the game, and this is the section which sets Mario into the long jump action. To simulate BLJs and solve them, we need to know exactly how Mario's position and velocity evolve during a typical long jump. Mario's position in 3D space is represented by 3 variables, X, Y and Z. The X and Z variables are Mario's horizontal position and the Y variable is his vertical position. So, despite Mario's model, his position is really just a single point at the centre of his feet. Here I'm running around in the game with the X, Y and Z variables visible. These variables are actually floats with a decimal component, but only the integer part is displayed in game. The same applies for pretty much all the variables I'll be using throughout the video. Mario's velocity is also a vector which has 3 components along each axis, and these velocity components determine how Mario's position changes every frame. And here are these velocities visible in game. So how does our velocity update every frame during a typical long jump? First, let's handle the vertical speed. Long jumping sets Mario's vertical speed to plus 30, thereafter it decreases by 2 every frame due to gravity. And this continues until our vertical speed becomes 0 and we reach a max height of y equals 240. And here is this being shown in game. Our X and Z velocities are not set directly. First, our combined horizontal speed is set. This h speed will become the most important variable in our analysis and we'll denote it as VH. A positive h speed means Mario's moving forward and a negative h speed means he's moving backwards. This h speed is so important that I'll use the Usamune practice ROM to replace Mario's life counter with his h speed, so it will always be visible in all footage I show you from now on. Once the h speed is set, our x and z speeds are updated via the h speed and our facing angle using trigonometry. Actually, the game uses lookup tables for trig functions which aren't very precise, and I'll be implicitly taking this into account whenever I use trigonometry from now on. How the h speed updates on every frame depends on what action Mario's in. There are 4 cases we need to consider. The first case is the most straightforward. On the first frame of a long jump, Mario's h speed is multiplied by 1.5. Here is the code that does this, and you might notice something interesting. The developers realised that this had the potential to lead to infinite speed gain, so they decided to introduce a hard cap. If Mario's speed after a long jump is ever more than 48, it gets set back down to 48. But this hard cap is only applied to forward speeds. The h speed can keep becoming more negative with no limit. This is the main reason BLJs work, but we're going to go into a lot more detail than this. Of course, under normal circumstances, Mario is airborne after long jumping and can't long jump again. So how does Mario's h speed update during his airborne frames? There are 2 factors: straining, which allows us to affect the velocity by using the control stick, and drag, which acts as a soft cap reducing the speed magnitude every frame. The straining depends on both how far the stick is held and the angle between the stick direction and the z-axis. Essentially, if you're holding the stick at the same angle Mario is facing, he will gain H-speed, and if you're holding at the opposite angle, his H-speed will decrease. And here is this forward straining shown in game. You can also strain perpendicular to the direction of motion, which adds some sideways displacement. But for now we're going to assume that our stick is held all the way up, directly opposite the facing angle. So during our BLJ, the effect of straining is just to decrease the H-speed by 1.5 every frame. And since our H-speed is already negative, this makes us move backwards faster. Drag gets applied after the effects of straining. We take our new H-speed after applying straining and bring it close to 0 by either adding or subtracting 0.35. Then, if the H-speed is above 48, it will be reduced by an additional 1. This gets applied on every single frame, so it's intended as a soft cap, reducing any forward aerial speeds back to 48. If our H-speed is negative, first 0.35 is added to bring us close to 0. And if our H-speed is still below minus 16, the game adds 2. Again, this is a soft cap intended to restrict our H-speed from becoming too large. But notice this soft cap is more strict for negative H-speeds than it was for positive H-speeds, possibly to make up for the lack of a hard cap for negative speeds. Now we can combine the effects of straining and drag. Given that our H-speed is negative and we're holding the control stick opposite to Mario's facing angle, we get this formula for how the H-speed is updated on every airborne frame. Notice that according to this formula, the H-speed will always fluctuate every frame. Here is the plot of H-speed for a single long jump, where we can see this behaviour clearly. After long jumping, our H-speed is multiplied by 1.5. Then the game adds 0.85 every frame as a result of straining and drag. Eventually the speed is brought within the range of minus 14 to minus 16, where it will oscillate until we eventually land. This is an effective terminal velocity for backwards airspeed, but unlike a hard cap, it's a soft cap with a range of values. Here we can actually see the H-speed fluctuating between minus 14 and minus 16 in game. We now know how the H-speed updates for 2 of our 4 cases. Actually, the case where Mario's just landed is simple. Since the collision check happens after the velocity updates, this is handled exactly the same way as an airborne frame. Now on to sliding. After Mario lands, he slides for 5 frames. On each of these frames, his speed is multiplied by 0.98, which acts as friction. Actually, looking at the code, this friction is only applied if the stick is not neutral. But we're going to be holding the stick up as we BLJ, so we should include this friction on every sliding frame. On each of these 5 sliding frames, we can instead input another long jump, anywhere from the first frame to the 5th frame. On our plot, we see that we land, slide for 4 frames, and then jump on the 5th frame. So this is how our horizontal speed changes every frame when we long jump backwards. Well, actually we made one slight error. Remember the straining and drag that we included for airborne frames? Well, that actually also gets applied to our long jump start frame, after the multiplication by 1.5. And finally, we know how the horizontal speed is updated on every frame. This is a simplified view of the game loop for Mario 64. And there are no more weird idiosyncratic things that developers put in the game. So when I tested this, I realized that the Z speed lags behind the H speed on every sliding frame. It seems like on the sliding frames, the X and Z speeds are updated before the horizontal speed, which leads to the X and Z speeds being set from the previous frame's H speed instead of the current frame's one. But taking this into account, our simulations match perfectly with what's found in the game. Before we move on, there's one misconception I want to clear up about long jumps. A big deal is sometimes made about the fact that there are 2 different animations for long jumps. A slow one if he starts with a speed less than 16, and a fast one if he starts with a speed more than 16. Notice his arms flailing around. But these are just animations and don't affect the physics at all. Now we're ready to move on. From now on, since the H speeds we're dealing with are always going to be negative, we're just going to flip this axis and just refer to H speeds as positive. This will make understanding a lot easier, because when graph goes up, we go faster, and when graph goes down, we go slower. So, What if, instead of being in the air for the full 30 frames, we somehow found a way to land faster before we lose all our speed to drag? These are the stairs leading to the 50-star door, but under that nice red carpet, it's really just a collection of wall and floor surface triangles. When I started investigating them, I found something a little disturbing. The stairs are slightly uneven, with the wall surfaces being either 25 or 26 units tall, and the floor surfaces being either 51 or 52 units wide. Luckily though, they follow a repeating pattern. This block of 5 steps is repeated, with each block having a total width and height of 256 and 128. Interestingly, these are powers of 2, which I assume was deliberate. This block is repeated 8 times, and then one final step brings us up to the 50-star door. The endless stairs leading to Bowser are similar, although annoyingly they have a slightly different pattern. This block repeats 14 times, and then 2 bonus steps take us to Bowser. So when I was double checking this, I found that the stairs ended 1 unit earlier than I expected. And I realised that this guy is 1 unit shorter than he should be, so spare a thought for him next time you run past. But before that, we have to get past this region, spanning 153 units or 3 steps. Entering anywhere in this region teleports us back 410 units, which is 8 steps. This is why these are called the endless stairs. But if we lock the camera, we can see what's really happening. So how does the collision work on all these floor and wall surface triangles? For learning about surface triangle collision, I highly recommend Pannenkoek's 3-part series Walls, Floors and Ceilings, which appears on his second channel, as well as this short video about invisible walls on his main channel. The links to all these videos will be in the description. I'll just quickly go over the main points. During ground movement, floor surfaces extend 100 units above and 78 units below the surface, whereas for air movement, they only extend 78 units downwards. If Mario enters a floor hitbox, he gets instantly snapped to the surface. But, as usual, things are a bit more complicated. When updating Mario's position at the end of a frame, instead of moving the full distance according to his speed, his movement is broken up into 4 quarter steps. If any of these quarter steps end up inside a floor hitbox, Mario gets snapped to the surface. If this happens during air movement, Mario lands, his Y velocity is set to 0, and the remaining quarter steps of that frame are cancelled. Wall surfaces have an initial check at the beginning of a frame and then 1 check on each quarter frame. The wall hitboxes are made up of 2 distinct parts. For the initial check and ground movement, the first hitbox is displaced by 30 units from the top of the wall and has a half width of 24, while the second hitbox is displaced by 60 units and has a half width of 50. For air movement, both hitboxes have a half width of 50, and the lower hitbox is lowered to 150 units from the top of the wall. Wall surfaces have a direction associated with them, and if Mario enters a wall hitbox, he gets pushed in this direction to the edge of the wall. This doesn't cancel our quarter steps for the frame though, so on every subsequent quarter step we're going to get pushed out again. Putting all this together, we get these combined hitboxes for the stairs. These ones for ground movement, and these ones for air movement. And now we're ready to exploit them. Let's see what happens when we long jump backwards up the steps. Since each step is 25 or 26 units tall and we gain 30 height on the first frame of a long jump, we normally jump cleanly over the step. But what if we jump very close to the step wall? At first glance it looks like we're just going to jump over it again. But quarter steps come to the rescue. It's interesting that the developers added quarter steps to try and stop us clipping into things and breaking the game, but they accidentally allowed one of the most famous glitches in all of speedrunning. In any case, after entering the wall hitbox, we get pushed back from it, and because wall hitboxes have a half width of 50, but each step is 51 or 52 units wide, we get pushed to 1 or 2 units into the step. Then the floor hitbox acts, so we get raised to the floor surface, landing and cancelling all our vertical velocity. Under what circumstances can we successfully clip into the wall? Intuitively, we expect that high speeds close to the next step should work, whereas low speeds far away from the next step should fail. I ran a simulation for each of these possible initial conditions, and I found exactly this behavior. The green area shows initial conditions where if the A button is pressed on the next frame, we will successfully clip into the stairs. Remember that for now I'm assuming that we're angled perfectly parallel to the stairs, and we're always holding up and Z on the controller. Let's try and understand this separating line, including this weird discontinuity. Since we move a distance equal to the velocity on our jump frame, you might expect that we just have to be this distance away from the step to get a clip. But we already know that the final quarter step can never clip into the wall because we're too high up. So the furthest away we can be from the wall is if our third quarter step lands inside it. We then get this condition for the distance in terms of the speed after the long jump, but we need to convert this into the velocity on the frame before. Luckily, I spent 10 minutes earlier deriving formulas for how the velocity updates on each frame. Remember that we had two parts depending on if the velocity was less than 9.9 or more than 9.9. So we finally know how close we have to be to the next step in order to ensure a successful clip on the next frame. Overlaying this line with our simulation results, we see a perfect match, including the discontinuity. But what region of this plot do we have to consider for our first clip? i.e., what is the minimum and maximum velocity of which we can start our first long jump? We've already seen that our terminal velocity during airborne frames fluctuates between 14 and 16. So the most velocity we can have to start our first long jump is if we land at exactly 16 velocity and then jump on the next frame. On the other hand, the lowest velocity with which we can start a long jump is if we land with 14 velocity, slide for 4 frames and then input a long jump on the 5th frame, which gives a minimum velocity of 12.913. So between this minimum and maximum velocity, we have the full range of initial conditions we can have on our first jump. Let's zoom in on this region. We see that if we're within 13.89 units of the next step, our jump will always successfully clip, regardless of the velocity. If we're between 13.89 and 17.36 units away, the clip will sometimes work, but this depends on our velocity, which is something we can't really change. So to 100% guarantee that our first clip will work, we need to input our long jump when we're less than 13.89 units from the wall. This is about a quarter of the width of one step, or if you prefer, about half of the step height. After we successfully catch onto the stairs with our first jump, how do we ensure that our further jumps will also be able to clip into the wall so we can gain speed? Let's see what a successful set of BLJs looks like. After the first successful clip, we landed at the edge of the step. Now we begin sliding backwards. When our intended position is inside the next step, first we check for wall collisions. But the ground movement wall hitbox is a lot thinner than for air movement, and usually we're not affected by it. But we do get raised up to the next step by the floor hitbox. And we continue sliding. Defining the frame where we performed our first clip as frame 1, we then have 5 sliding frames, 2 through 6. Instead of just sliding, can we input another jump on one of these frames to clip into the steps a second time? The first frame has A held because that's the frame where we've jumped. We can't jump again immediately because we have to release A for at least one frame. We could input another jump on the third frame, but usually we're too far away from the step to clip inside it. However, if we slide for one extra frame, and then input a jump on the fourth frame, this will usually clip again, instantly landing and gaining another burst of speed. Now we're sliding again, but considerably faster. We have to release the A button on the 5th frame if we want to jump again. But on the 6th frame, we can jump a third time, and this time we are close enough already to get the third clip. Looking at the H-speed plots during the first 3 clips, we see that each clip provided a large amount of speed. I'll soon prove that just 3 clips like this is enough to guarantee that any further jumps will always gain speed. We'll call this a 146 BLJ because these are the frames on which we jumped. And here's what it looks like in game. But apart from 146, are there any other solutions? Well, there's another common solution, which is 148. Here, instead of jumping on the 6th frame, we slide on the 6th and 7th frames and get our third clip on the 8th frame instead. Here's the H-speed plot of this, and here's it happening in game. These 146 and 148 solutions were popularized by a tweet from Weegee, and Zandre64 then created a Python program to help you press A on these frames consistently. And this was ported to N64 by rollercobester. However, as far as I know, these solutions were first pointed out by Plush in this video 7 years ago. So we know that these 146 and 148 BLJs usually work. But do they always work? And what about other solutions? To test all the possible A-press combinations, we're going to take a representative sample of all the possible initial conditions that can lead to the first clip. Then we're going to see how they evolve frame by frame within this plot. This space showing all the possible positions and velocities is what a physicist might call phase space. So we're going to be studying various different possible phase space trajectories. First we need to make one correction. Previously we've assumed a binary success criteria where either we clip into the next step or we don't clip and lose speed. But there's a third possibility. If we're moving fast enough, we can land further up the stairs with a net increase of speed even without a clip. You can see this happening here. Here our speed is 28, but after jumping, we land with 33 speed. If we allow for this possibility, we get this corrected success region. I've taken a pessimistic approach where it only counts as success if we can jump, land and slide for 4 frames and the speed is still higher than we started with. So it turns out we only need to get a speed of about 28.4 before subsequent BLJs will always gain speed. For context, our starting speed is down here in this range. We just need to perform enough successful BLJs in a row to bridge this gap, then we can build up infinite speed by chaining long jumps on any frame. How many BLJs do we need before we have enough speed? Well, before our first jump, our speed is between 12.913 and 16. Our maximum speed after the first clip is then 1.5 times 16 minus 0.85 for drag, for a total of 23.15, while our minimum speed is 1.5 times 12.913 minus 0.85 for drag, and then 4 sliding frames, for a total of 17.082. Doing the same procedure, we can find the speed range after 2 clips. Interestingly, 2 clips is sometimes enough to get us into the success region, but it doesn't guarantee it. However, the speed range after 3 clips clearly shows that we will always be in the success region. This means after getting 3 clips in a row, any further jumps will always gain speed. This is the proof that the 146 and 148 combinations we showed before are sufficient without considering when the 4th jump happens. Given that 3 successive clips are enough to guarantee success, there are only 16 possible A-press combinations that we have to analyze. The first A-press happens on frame 1 by definition. The A button then has to be released for at least 1 frame before it can be pressed again on frame 3, and at most we can wait until frame 6. For each of these 4 choices there are another 4 choices for the 3rd jump frame, giving 16 total A-press combinations. Now, let's finally do our phase space analysis to see which of the combinations work. Our current frame number and our A-presses will be shown in the top left. We're going to take these 2,500 initial data points and see how they evolve as we go frame by frame. On the first frame, we press the A button and get our first clip. We always end up at the edge of the next step. Then, we slide along the step as we release the A button. These are the possible positions and speeds on the second frame. Now, will pressing A on the next frame, i.e. frame number 3, gain speed? Well, the majority of points here lie in the red region. So no, usually we can't get a clip on the 3rd frame. only 2.5% of the possible initial conditions work. This isn't very good, so let's keep going on to the next frame without jumping. Here, on the third frame, 99.9% of the points are in the success region, so a jump on the fourth frame will almost always work. This is a vindication of the 1-4 A-press strategy found by Plush. But interestingly, there's a very small chance that this strategy fails. But this only happens in 1 out of 1,000 possible initial conditions, so it requires very bad luck. And no one has ever been that unlucky in a speedrun before.
What the hell?
Anyway, let's see what happens if instead we slide on the fourth frame. Now, all the points are in the failure region, which means a clip on the fifth frame will never work. But if we carry on sliding, most of the points on the fifth frame end up in the success region, but it's not very consistent. In total, 58.5% of the points will lead to success if we jump on the sixth frame. Let's put all this together. An A press on frame 4 will almost always work. An A press on frame 6 will work just over half the time, whereas a press on frame 3 is very unlikely to work, and a press on frame 5 will never work. Now let's go on and see what happens on those rare occasions where 1-3 combinations work. What frame do we have to input our third jump on? Here are the points for all the frames 1 through 5. We're going to take the small percentage of points where a jump on the third frame works, and see how they evolve after the clip. So we jump on the third frame and clip into the next step. Now you'll see that as we slide, all the points are always in the success region, regardless of which frame we input our third jump on. 1-3-5 works, 1-3-6 works, 1-3-7 works, and 1-3-8 works. This is what we meant before when we said that sometimes 2 clips is enough to guarantee speed gain. After getting 2 clips on frames 1 and 3, subsequent jumps will always gain speed. Although getting the clip on frame 3 was very unlikely in the first place, so this isn't that useful. Let's move on to the case where we get the clip on frame 4, which is much more promising. We will take the 99.9% of points that work and see how they evolve. We jump on the fourth frame and clip into the next step, and after sliding for just a single frame, we're always in the success region. So a jump on the sixth frame will always work given clips on 1 and 4. This is the 1-4-6 combination that we first analysed. If instead of jumping we slide on the sixth frame, here half our points are in the success region, so a combination of 1-4-7 will sometimes work but isn't consistent. But if we slide for another frame, all our points are in the success region again, so a jump on frame 8 will always work. If we slide on frame 8 and try and jump on the 9th frame, this will sometimes work but is even less consistent than 1-4-7. For comparison, here are all the sliding frames after clipping on frames 1 and 4. On frames 5 and 7, we're always in the success region, so jumping on the next frames, 6 and 8 respectively, will always lead to the third clip, whereas all the other combinations are inconsistent. So 1-4-6 and 1-4-8 are definitely the best, but let's just quickly go over the remaining combinations. We take the 58.5% of points that will lead to a clip on the 6th frame and see how they evolve. The 1-6-8 combination will always work given a clip on frame 6. The 1-6-9 combination will sometimes work. The 1-6-10 combination always works, and 1-6-11 sometimes works. So we finally have scores for all the possible A-press combinations, where the 1-4-6 and 1-4-8 combinations emerge as the clear winner. By multiplying the scores for the second and third clips, we get combined scores for each combination. It should be stressed that these scores shouldn't necessarily be viewed as a probability of success, because we didn't look at how likely each initial condition was to occur, but they suffice to show that some combinations are definitely better than others. So we've conclusively proven that pressing A on frames 1-4-6 or 1-4-8 is definitely a good idea. And we have a very simple 2-part recipe to get consistent BLJs. Number 1, land less than 13.89 units from the next step. And 2, press A on frames 1-4-6 or 1-4-8. You might notice that this requires pressing A at uneven intervals. Does this mean that mashing A at a specific BPM is bad advice? A clue is given by the fact that the 147 combination is the only decent solution that has equal spacing between presses. Both of our best solutions have unequal spacings between A presses. So does this mean we can never get them with a consistent button mashing speed? Well, the reality is a bit more complicated. When we press the A button, it isn't a discrete process, but a continuous one. We can press and release the button at any time, not just at the frame intervals. Let's consider these A presses, where the blue squares indicate when the A button is pressed and released. Since the game runs at 30 FPS, each frame lasts for 33.3 milliseconds. And at the beginning of each frame, the game polls the inputs and determines whether A is considered held for that frame. So on frame 0, the A button is not held. On frame 1, the A button is held. Then the A button is released, so on frame 2 it's not held, and no A press on frame 3 either. But there is an A press on frame 4. Let's see what happens if we take our 148 presses and shift the first and third press to be half a frame earlier. The end result is the same as far as the game's concerned. It still considers A to be held on frames 1, 4 and 8, but in terms of real time, there's a consistent time delay between each A press. In this case 3.5 frames, and the first A press is offset from the frame alignment by half a frame. We can even achieve the 146 press, this time with a delay of 2.5 frames. By varying the number of delay frames and the offset, we can get a whole host of different A press combinations, even with a consistent mashing speed. First, some sanity checks. With a 2-frame delay between every press, we get the 135 combination. For a 3-frame delay, we get 147, a 4-frame delay 159, and a 5-frame delay 1611. But between these integer values, we can get a whole host of other combinations. Let's add on the scores that we calculated earlier. We can get 148 some of the time with a delay of 3.5 frames, but since the offset is effectively random, half the time we get 158, which never succeeds. Our average score here is then around 50%. Similarly, we can get 146 some of the time, but half the time we get 136, which only has a 2.5% chance of working. So on average, our score here is only about 51%. We can actually get a better score by just choosing a delay of 3 frames. This always gives 147 and has a score of around 55%. Really, any delay between 2.5 and 3.5 will give a score of roughly 50%. We can see this more clearly if we average over every offset value. It looks like there's only a few data points here, but the curve is just naturally disjointed like that. As expected, there's an optimal mashing region which gives roughly the same results. So it seems like we don't have to be too precise with how fast we mash the A button. Let's convert these plots into the number of A presses per minute, i.e. the BPM of our button mashing. And we find that the optimal mashing speed is between 514 and 720 BPM. If we average over the random offset values, we conclude that the best button mashing speed is 600 BPM. This was already the accepted answer, as discovered by JS64 using a separate methodology to mine. But we now know that this condition is not so strict. In reality, we can mash with a BPM anywhere between 514 to 720 and achieve pretty much the same results. In fact, looking at the successful BPM values found by JS64, as well as the 600 BPM values that he pointed out, which are equivalent to the 147 A press combination, there are also values around 514, which would have been the 148 presses, and some values around 720, which would have been the 146 presses. In fact, the vast majority lie in our optimal range between 514 and 720. Mashing any faster than this will start to give worse results. But unless you're, say, the fastest button masher in the world, you probably aren't mashing that fast. So what about the 450 BPM speed that was originally recommended by Zombie? Interestingly, this is the only possible BPM that theoretically should never work, because this is equivalent to the 159 press that had a 0% success rate. But of course, this makes a lot of implicit assumptions. In reality, humans can't mash perfectly, so a human BPM would actually take a range of values. Furthermore, the game doesn't always run at exactly 30 FPS. Even a tiny amount of lag during a frame can shift an A press from one frame to another. So while 450 BPM won't have an exactly 0% success rate, we should still find that a lower speed of 400 BPM will be better. To test this, I wrote a Python script using the library PyInput, which allows me to set an exact BPM value of my A presses. I then measured how many successful BLJs I could get on the endless stairs in 5 minutes, making sure to take multiple trials so I could get a reliable mean and standard deviation. Here are the raw results for each BPM I tested. And here are the mean values, showing the uncertainty in the measurement. As expected, 400 BPM is not great, but is significantly better than 450 BPM, while 514, 600 and 720 are all pretty comparable, with 600 BPM coming out on top. We can also convert this into the average number of seconds it takes to get a successful BLJ, where we find that there's really not much separating the three highest speeds. So you might want to take this into account the next time you're doing BLJs. Of course, some people are much better at mashing a consistent speed than others. So mashing at 600 BPM is generally good advice, but mashing at 450 BPM is sadly not. What about the rest of this advice? Should we start mashing A the moment we hit the stairs? Well, we know this isn't really required. To get a clip, we just need to be within a certain distance of the next step, and this could happen on any sliding frame, not just the first one. But starting to press A as soon as we land will help a lot with consistency, and means we don't waste A presses in the air where they won't do anything, which will just tire us out. So in general, I think this is good advice. Whether you should mash A as fast as you can obviously depends on how fast you can mash. Faster is not always better, so I don't think this is good advice. Now, all this analysis was done assuming that we're perfectly parallel to the stairs, and we're straining perfectly opposite Mary's facing angle. What happens if these assumptions break down? When we perform our BLJs, we aren't always perfectly aligned with the stairs. Usually our angle is relatively minor, but it could also be pretty large. But I always wondered, in this situation, should we carry on straining aligned with our facing angle? Or should we strain along the stair direction, regardless of which way we're facing? Previously we'd only considered forward and backward straining, but now we're going to add a sideways straining term, changing our X and Z velocity update functions slightly. And I should mention that the game stores angles as short unsigned integers, with values between 0 and 65,535. Here our facing angle is 32,208, and here our facing angle is 29,739. But what the heck do these numbers mean? As always, I recommend a video on PannenCoic's second channel about angles. All we really need to know is that 32768 in-game units is equivalent to 180 degrees. So our first angle was roughly 177 degrees. Perfect alignment is 180 degrees, since we're facing backwards. So in other words, this is 3 degrees off of perfect alignment. While the second angle we looked at was 17 degrees off perfect alignment. And remember that every time we do trigonometry with these angles, we should use the in-game lookup table. Our success plot is slightly modified when we BLJ in an angle. Not all of our horizontal speed is directed along the z-axis anymore, and this makes the separating line of our success plot a bit steeper, i.e. it becomes harder to clip into the stairs. However, this is with still straining opposite our facing angle. Maybe we can do better if we strain along the stairs. In this case, as well as the increased steepness of the curve, it also gets shifted to the right. The former means it's harder to clip into the stairs, and the latter means it's easier to clip into the stairs. So which wins? Should we start BLJing at an angle to increase our chance of success? If you recall, the critical distance we had to be from the next step to get our first clip was 13.89. This is how that value changes as we increase the BLJ angle, for both straining strategies. It's clear that since the critical distance decreases, BLJing at an angle does not help us get a successful clip. However, it's remarkable just how tolerant the trick is to our angle. Straining along the stair direction is definitely the better choice, and a pretty huge angle of 20 degrees doesn't really affect the critical distance at all. So, BLJing at an angle doesn't help the first clip, but maybe it helps subsequent clips. Let's look at the combination scores and see how they're modified. A clip on frame 3 remains very unlikely. Our best combinations of 146 and 148 remain almost perfect, even with very large angles. The score for 147 decreases quite a lot as we increase our angle. Even for a small angle of 5 degrees, it's noticeably worse. And this is quite important, as this is the combination we get if we mash at 600 BPM. The score for 149 increases somewhat for small angles, but it's really nothing to write home about. A clip on the 5th frame remains impossible despite our angle, and the scores for clipping on the 6th frame strictly decrease. So long jumping at an angle doesn't really help, but it doesn't really hurt much either as long as the angle is small. Another source of potential randomness I haven't mentioned yet is the fact that the stairs have different widths and heights. Until now, all the results I've shown you have been assuming that we've started from the bottom step like this. But really, we should make sure that our analysis is still true if we clip it to any step. Luckily, due to the repeating pattern, we only have to check 5 unique steps. This is our success plot from the first step. As we look at the other steps, our main separating line won't change at all. Actually, when I was deriving this line, I never used the exact step height, only the fact that it was between 22.5 and 30 units. This other line will change slightly, but the change is so minimal you probably won't even notice as I go through the steps here. The actual scores change more since the differing step widths lead to different face-based trajectories. Here are the scores for each of the 5 unique steps of the 50-star stairs. Thankfully, all our conclusions are still valid. The 146 and 148 solutions still have 99.9% success rate, and even 100% in some cases. And remember, the steps for the endless stairs followed a slightly different pattern, so here are the scores for those. Once we've built up speed using our BLJs, what comes next? So after we've built up speed, why do we clip through the wall? And how come we sometimes lose our speed on the other side of the wall, but other times go shooting straight through? And what exactly is going on here, where we build up speed by just jumping up against a wall? Let's deal with this last question first. Did you know it's possible to gain speed from BLJs on flat ground? Here I've hacked my speed to be 73, and I'm going to long jump, and we land with 83 speed. We gain 10 speed just from BLJing in the air, and each subsequent BLJ will gain even more speed. So what's happening? Well, assuming we're straining opposite to our facing angle, we can only lose at most 0.85 speed per frame. So if we start with enough speed, we can land with greater than or equal to our original speed. But what speed is enough for this to happen? This is a formula for our landing speed, based on our starting speed and the number of frames we're in the air. We can easily find the condition for when we gain more speed than we lose. So the 2 ways a BLJ can gain speed are 1, if we land quicker, i.e. decreasing the number of airborne frames. This is like when we land on stairs or a slope. But 2, we can also gain speed if we simply start with a faster speed to begin with. This is what happens when we BLJ against the wall of the 50-star stairs. On flat ground there are 30 airborne frames, so we find that our critical velocity on flat ground is 52.7. As shown here, if we start with 52.7 speed, we land again with exactly the same speed. However, we can only gain speed here if we jump on the first frame. Here I'm showing what happens if we get a 5th frame jump instead. To guarantee speed gain even on 5th frame jumps, we need a bit more speed to start with. After modifying our formula to account for these 4 extra sliding frames, we get this new condition, and a critical velocity of 63.37. Now we can gain speed even if we get 5th frame jumps every time. In this case, I landed with only 57 speed, so I needed to get a 1st frame jump here in order to gain speed. Thankfully I got it and eventually was able to get through after just 18 jumps. An uncomfortable truth is that there's no maximum number of jumps it takes to get through. The closer our starting speed is to the critical values, the more jumps it will take, approaching an infinite number as we get closer and closer to the limit. Now let's analyse these walls. This wall is actually made up of 2 parts. There's one surface here on this side of the stairs, and another surface on the other side. If you recall from earlier, each wall has 2 hitboxes for air movement, an upper one displaced by 30 units, and a lower one displaced by 150 units. So the combined hitbox looks like this. Usually the fact that there are 2 hitboxes doesn't matter because after getting pushed by one, we can't get pushed by the second one. But keep this in mind for now, it will be important soon. The two sides of our wall are separated by 103 units, and adding in the hitboxes, we get this picture. First, let's see what happens if our speed is less than 400. Our first quarter step ends up in the front wall hitbox, so we get pushed back by the wall but keep our speed. If our speed is between 412 and 812, our quarter step ends up in the back wall instead, so we get pushed through to the other side. But we lost our speed after getting through. Why did that happen? Well, it turns out that whenever we get pushed backwards through a wall hitbox, the game sets our speed to 0. You can see this here in Bob on Battlefield, where we enter a wall hitbox from the wrong direction. If we go forward through it, we keep our speed. But going backwards through it resets our speed to 0. You see, if we collide with the wall hitbox while facing in the direction it's pushing us, we keep our speed. But if we're facing towards the wall, 3 things can happen depending on our speed. If our speed's above 38, we hard bonk. Else if our speed's above 16, we soft bonk. And if our speed's below 16, our speed's set to 0. When we go through this wall backwards, we're facing the wall, but our speed's negative, so it's below 16, and that's why our speed gets set to 0. Here's the actual source code that handles all this behavior. Thus, during BLJs, if we get pushed by the front wall, we keep our speed, and if we get pushed by the back wall, we lose our speed. If our speed's large enough, i.e. more than 812, our first quarter step lies beyond the second wall, so we never get this push from the back wall, so we can keep our speed. But what happens if our quarter step ends up in this 3 unit gap between the wall hitboxes? Well, this happens. Our speed got set back to 0 for seemingly no reason. If we use hacks to remove this wall, we see that there's no floor surfaces between the 2 walls, i.e. this area is out of bounds. So now we know what happened. Our quarter step ended up out of bounds, so the game set our speed back to 0.
Eventually. Alright, well.
Here's a summary of all this information. We don't really care which of these outcomes we get, as long as it's not this one. Also note that these speed values assume that we're starting the frame at the edge of the wall. If we're coming in from further away, the speed values will change. So we need 412 speed to get through the wall. What about clipping through the door itself? The door is actually made up of 2 separate objects, with each side having a width of 160, height of 256 and a depth of 40. Each door is just made up of 2 wall surfaces, 40 units apart. This is much closer together than we saw for the side wall. In fact, they're so close together that their wall hitboxes overlap. Notice there's a 60 unit overlapping region where both hitboxes are acting at the same time. Before we go any further, I should mention that this diagram is very oversimplified. In reality, there's another set of walls above the door which make up the whole doorway. So here's a more correct picture, except that each wall's lower hitboxes are displaced 150 units downwards. There's also a ceiling here whose hitbox descends 160 units. So it goes without saying that a lot of strange behaviour can happen with all these hitboxes interacting with each other. However, usually we're within 106 units of the ground, so a simplified view will suffice. So what happens if our first quarter step ends up inside this weird overlapping hitbox? Both hitboxes try to push us simultaneously, so adding the vectors together, we end up on the equivalent point on the other side, as if there was a mirror at the centre of both walls. But that isn't the end of the story. Remember that each wall has 2 hitboxes. First we handle the first hitbox of both walls, which we've just done, but then we need to handle their second hitboxes. So we get pushed again by these hitboxes, and end up mirrored again back to the other side. If you're paying attention, you'll realise that the combined effects of all these different wall hitboxes is absolutely nothing. We ended up right where we started. So we just carry on with the rest of the quarter steps. In this case, our next quarter step ended up in the back wall, so we got through to the other side. Thus, we only need 160 speed to clip through the door, compared to 400 to clip through the sidewall. In this case we lost our speed after clipping through, but is that always the case? What about here? Both our first and second chord steps landed in the overlapping hitboxes, so they cancelled each other out both times. Did this count as us getting pushed by the back wall or not? Well, sometimes we lose our speed, but sometimes we don't. What's going on here? You see, when we interact with multiple walls in a single frame, only the most recent wall is returned and used for interactions. This can lead to some wall behavior being missed. This is usually referred to as unreferenced walls, although I tend to prefer K's name for it. In our case, if the front wall happens to push us second, we keep our speed, but if the back wall pushes us second, we lose our speed. Because these doors are made up of many different wall surfaces, whether or not we lose speed as we go through seems to depend on where on the door we clip through. Here's a table of what happens as we try to clip through the door at different speeds. Unlike the side wall, it seems like there's no way to randomly lose our speed without clipping through. But life is cruel. This table is all assuming that we're starting the frame at the edge of the wall, but on our first approach to the door, a tragic sequence of events can occur. We randomly lost our speed out of nowhere. Sometimes, for a few frames, you can even appear to be on the other side of the door before the game pushes you back. This happened to Bubsya in his recent blindfolded 0-star world record.
It sounded very strange. What happened to it?
Well, let me explain. Take this scenario. Our first 3 chord steps all landed in free space off to the left, but our fourth and final chord step landed in the overlapping hitboxes. We got pushed by both walls, and we interacted with the back wall last, so we lost our speed. But this was the last chord step of the frame, so we ended the frame sandwiched between the 2 walls. So what pushed us back out to the front? Well, we haven't had to use them yet, but remember that wall hitboxes have an initial handler before any chord step movement, for precisely this kind of situation. First we get pushed by both walls with a half width of 50, but then we get pushed again by both walls with a much thinner hitbox of half width 24. The first of these hitboxes act the same way we've seen before, mirroring us to the other side, but then the thinner hitboxes act, and it's these hitboxes that push us out. Then the chord steps happen and we get pushed back even more. This only happens if our final chord step lands in the back half of this overlapping region. If it landed in the front half, we'd clip through to the other side instead. So quite a lot has to go wrong for this to happen. But what happened to Bubsya? He didn't get pushed back immediately on the next frame. We saw him through the door for a few frames before he got pushed back.
He's through, but it's like some weird quarter frame shit where the game still thinks that you're on the other side.
Yeah, basically. His final chord step landed exactly in the 8-unit window where even the initial wall boxes overlap. So in this case, those hitboxes cancelled as well, and he remained stuck between the 2 walls. If we're standing still like this, it's obvious we're between the 2 walls. But if we're long jumping, Mario's model gets pushed back slightly, and it looks like he's through the wall, but he's not. If we hold up and try and go through the wall, we get pushed by the initial hitboxes to the opposite direction. To summarise, it takes much less speed to clip through the door than the side wall, and it also seems safer. We can lose speed on the side walls while BLJing up against them, while losing speed on the door only seems possible on the first approach. For this reason, I recommend aiming to clip through the door rather than the side walls. Although, as I mentioned, this area is quite complicated to analyse, so I'm not ruling out that there are other circumstances in which we can lose speed here. I thought I was done with this door, but then I noticed something weird. The 2 door objects actually overlap by 6 units. We can actually see this with our eyes if we look closely. The seam between the doors isn't exactly at the midpoint. If we push them 3 units further apart, it looks like the models are lined up now, but the actual collision surfaces are still overlapping. Pushing them apart another 3 units makes them flush against each other. But now there's a noticeable gap in the models. It's like they made the models too small for the hitboxes they had and just decided to push them closer together. This can lead to some strange effects. For example, here I needed close to 250 speed to clip through, whereas normally it would only require 160. The overlapping region is pretty small though, and easily avoidable, so that's what I recommend doing. In contrast, clipping through the endless stairs is easy. There's no quarter-step checks for the warp region. We just need 153 speed to get past it. Although this requires a perfect position at the start of the frame, so in practice you'll need a bit more than 153 speed. We're almost done. We just need to do some quick troubleshooting. You've probably been in this situation where you seem to lose your jump out of nowhere. People will often tell you, make sure you're holding Z the whole time. While this is obviously true, this is not the reason most people lose their jump. Let's see what really happened. Here, we press A on frame 1, jumping and clipping into the step. But A presses are rarely just contained within a single frame. Here A is held a bit longer, so it counts as being held for frames 1 and 2. This eats up our first sliding frame. Then A has to be released for at least a frame before you can jump again. This eats up a second sliding frame. So there are only 3 frames we can jump on instead of the usual 5. And if we press A just a tiny bit late on that last frame, it won't count. So the real reason we lost our long jump is that we simply missed the A press. But this is an easier mistake to make than it first appears. Sometimes, while BLJing on the endless stairs, you'll get stuck. This is due to our speed becoming so large that our quarter step goes beyond the neighbouring floor hitboxes. If you react fast enough, you can back this up by releasing Z to stop long jumping, holding down on the control stick, then gently pressing A to gradually lose speed. If this happens to you, you're bad at the game. You clipped through this left wall and ended up down there in the wet dry world painting. Just don't angle your long jumps to the left. Looking at the list of advice that we started with, we see that a lot of the conventional wisdom was proven correct, but we did manage to debunk some of the more spurious advice. Here is my own personal list of recommendations. A question I'd like to address in the future is there any way to always land within 13.89 units of the next step? Certainly, runners like Green Suigi already do this, and that's why their BLJs are so consistent. But is there a method that anyone can learn? Together with consistent 1-4-8 A presses, we could be close to an age where anyone can BLJ consistently. Thanks so much for watching. Please support me if you can. There's a donation link in the video description. I'd like to give special thanks to Pannen and the whole ABC crew, the STROOP development team, the Mario 64 Decomp team, as well as all the people I've mentioned throughout the video. All the resources I used will be linked in the video description. Thanks again, and take care.